Of the three kinds of hazards, structural, data, and control hazards are the most difficult to deal with in the pipeline. This video is about control hazards in the pipeline, but first let us answer some questions about structural and data hazards. Since pipelines do not like control hazards at all, there are a whole host of techniques to handle control hazards. In this video, we are going to see what control hazards are and various mechanisms to handle control hazards. Some of the techniques to handle control hazards are quite advanced and are beyond the scope of this particular course. Even those that we are going to discuss in this video are quite subtle, so pay close attention. First, let us see what control hazards are. A control hazard is nothing but a situation where the pipeline cannot operate normally due to non-sequential control flow. That is, in any normal program, you are going to have control flow which is not necessarily sequential. That is, you are going to have conditional and unconditional branches. When these instructions come into the pipeline, the mere possibility that there is going to be non-sequential control flow can cause the pipeline to not operate normally, and these are control hazards. Let us take this example to illustrate. We have a sequence of 4 instructions. First an add, then a branch equal, third a subtract, and fourth a load word. Note that the subtract and load word instructions are in the branch fall through. That is, they will be executed when the branch is not taken. In this example, can you tell in which clock cycle the branch equal instruction will know whether or not the branch is taken? According to the scheme of things we have been talking about, the branch equal takes 3 cycles. That is, in this example, it will take until the end of clock cycle 4 for the branch condition to be determined. In other words, until the end of clock cycle 4, we do not know what is the instruction to be executed subsequent to the branch equal instruction. This essentially means that the instructions following the branch equal, sequentially following the branch equal, should not potentially be entering the pipeline when the branch condition itself is not known. That is, the normal operation of the pipeline tells that this subtract instruction must be fetched in cycle number 3 and the load word instruction must be fetched in cycle number 4. This is not possible due to the control hazard. So intuitively, we feel that since the execution of the subtract and load word instruction should depend on the branch condition, which is known only by the end of clock cycle 4, they should not enter the pipeline before that. One simple solution, so-called solution for addressing this control hazard is to stall. Now, can you tell for how many cycles should we stall the pipeline in order to resolve this control hazard? Well, since the branch condition is known only at the end of clock cycle number 4, that is, we have the correct value of the PC for the instruction to be executed after the branch equal only by the beginning of clock cycle number 5. Until then, we cannot really fetch any instruction. That is, we have to stall for 2 cycles. This diagram shows a case where the branch is not taken. So the instructions sequential to the branch equal are stalled. The subtract instruction enters the pipeline only in the beginning of clock cycle number 5, and then the subsequent load word enters in the next cycle, clock cycle number 6. Note that this pipeline timing diagram would also be valid had these instructions been from the branch target and the branch had been taken. So here is a question. Suppose 10% of the executed instructions are branches. What is the performance implication? For each branch instruction, 2 bubbles enter the pipeline. So the CPI is going to increase from the ideal value of 1 to 1.2 due to control hazards. So that is why this stalling solution is a solution only from the correctness perspective. It is not really a solution from an efficiency perspective, because an increase of CPI from 1 to 1.2 sounds quite expensive. Well, even in this simple example, I have run out of slide space for showing this load word instruction. So this much inefficiency is not acceptable in practice. So whenever we encounter a branch in the sequence of executing instructions, there is a branch penalty. This penalty is in terms of 2 bubbles entering the pipeline. that is 2 cycles in which no meaningful instruction is completed from the pipeline. Since this 2 cycle branch penalty is too expensive, there are a whole host of techniques which we can employ to reduce the branch penalty. We are going to look at these techniques one by one, and as I said, many of the techniques are beyond the scope of this course. Let us first look at this technique of reducing the number of stages taken for the branch to 2 stages from the original 3 stages. The problem with encountering a branch in the pipeline is that we do not know what instruction must execute after the branch until the branch condition is determined. So we ask the question whether we can reduce the number of stages taken for the branch condition determination from 3 stages to 2 stages. Think about this and tell what extra hardware may be required to achieve this 2-stage branch completion. In comparison to the 3-stage branch completion, we are going to need an extra comparator in stage 2 itself. In the 3-stage execution plan for the branch instruction, we use the ALU itself as a comparator, subtracting one register from another. This would not be possible if we want to achieve a 2-stage branch completion. So we will need a special comparator hardware in stage 2 which compares the values of the 2 registers which have been read. Now put this together with what we said about the register file when we handled data hazards and think about how much time this comparator has in order to complete the comparison. Since we arrange the register file such that it needs to write in the first half and read in the second half, we really have only half a cycle in which to finish this comparison operation. Well, this is with respect to the extra hardware that is required. Not only is extra hardware required, this solution is also going to introduce further data hazard implications. The additional data hazard implications arise because earlier we required register values only in stage 3 or stage 4, that is in the EX or MEM stages. Now, if we have 2-stage branch completion, we are going to need register values even in the ID stage in the case of branch instruction. So this essentially means that we need extra forwarding. Now we are going to need forwarding to the ID stage as well for the branch instruction. Well, there is actually another implication as well. Since we are going to need the data, the register value, one cycle earlier, there is a possibility that the branch instruction itself may stall due to data dependence on an earlier instruction. The working of this 2-stage branch completion and the implications are best understood in terms of a couple of examples. Let us look at those now. First, let us understand how the 2-stage branch completion helps. In the same example as earlier, now with the 2-stage branch completion, how many cycles of stall are going to be required before the next instruction to be executed is loaded into the pipeline? Well, with a 2-stage branch completion, in this example, in clock cycle number 3, by the end of clock cycle number 3, we are going to know the branch condition as well as the next valid value of the PC. So clock cycle number 4 is when we can fetch the next instruction to be executed. So there is one bubble entering the pipeline per branch instruction instead of 2. So let us now answer this performance question again. Suppose 10% of the executed instructions are branches. What is going to be the performance implication? In this case, the CPI will increase from 1 to 1.1 because one bubble enters the pipeline for every executed branch instruction. This is better than CPI increase from 1 to 1.2, but it is still not so good. This slightly modified example illustrates the data hazard related implications of the 2-stage branch completion. Note that in this example, one of the registers used in the branch comparison is a result of the execution of the prior instruction. In this case, what do you think is going to happen to the various stages of the branch equal instruction? The branch equal instruction is going to stall in its ID stage. It will enter the pipeline, and then in its ID stage, it will realize that the register to be used is not yet available. It is available only by the end of clock cycle number 3, and even then a data forwarding is required in order to get the required value. Now can you tell from which latch to which stage we are going to need the data forwarding? We are going to need the data forwarding from the EXMEM latch, which is where this value is available, the required value is available during clock cycle number 4, to the ID stage, which is the stage in which the branch equal instruction is in clock cycle number 4. So the ID stage which was done for the branch equal instruction in clock cycle number 3 is cancelled out on realizing that in clock cycle number 3 the correct value of R1 is not available. Now in which clock cycle can the next executed instruction after the branch enter the pipeline? It can enter the pipeline in clock cycle number 5. This is because the 2-stage branch completion completes only by the end of clock cycle number 4 in this example. Well, if you realize now, we are back to the situation where the load word 5th stage is going out of my slide. We have introduced 2 bubbles in the pipeline. This time, one bubble due to data dependence of branch equal on the result produced by the previous instruction, and another bubble introduced after the branch. Well, in many programs, it is common to do set less than, for example, just before the branch equal instruction, and then do a branch equal instruction, in which case there will be a data dependence. So even though we reduce the number of cycles required for branch equal from 3 to 2, we are back to the same situation in terms of overall performance. Not looking good, not looking good. Let's see what else we can do. Let us now look at the next technique to reduce the branch penalty, which is assuming branch not taken. Before that, make sure that you understand the 2-stage branch completion solution, its extra hardware requirements, its various implications, the situations in which it helps, the situations in which it does not help. Assuming you have understood, let's move forward. One simple thing which we can do to reduce the branch penalty is to always assume that the branch is not taken. That is, we are going to let the instructions sequentially following the branch instruction to enter the pipeline under the assumption that the branch will not be taken. Well, if we make an assumption, we have to check whether the assumption was correct or not. In which clock cycle in this pipeline timing diagram will we be able to check whether or not the assumption of branch not taken was correct? We will be able to check that in clock cycle number 4, because only by the end of clock cycle number 3 is when the branch condition is determined. Now suppose the assumption of branch not taken were wrong, that is, the branch were actually taken. In clock cycle number 4, suppose we know that the branch were to be taken, what do? We have to cancel out the instruction which is currently in the ID stage. That is, this subtract instruction would have to be cancelled out. Note that the instruction which is in the IF stage in clock cycle number 4 would be the correct one to execute next. This is because irrespective of whether the branch is taken or not, in clock cycle number 4 we have the correct PC value, and hence the instruction which is in the IF stage in clock cycle number 4 is indeed the correct one in the pipeline. So we only need to cancel out the instruction in the ID stage which has entered wrongly in the case the assumption was wrong. So just to check if you understand what is going on here, here are a couple of questions. First, how does this technique reduce the branch penalty? Well, it reduces the average branch penalty because in some cases the assumption will be correct and in some cases the assumption will be wrong. In cases when the assumption is correct, we introduce no extra bubbles in the pipeline, so we are good. In cases where the assumption is wrong, this cancelled out instruction will correspond to a bubble in the pipeline, and that is when we are back to the same old situation where there is a bubble in the pipeline due to a branch. Here is another question. What do you think of the effectiveness of this solution in reducing the number of stalls for loops in the program? For long running loops, this technique does not really help much because most of the cases the branch is going to be taken from the end of the loop to the beginning of the loop. This means that the assumption will be wrong most of the times. That is, this particular technique has pretty much no performance benefit for long running loops. Not only that, we have a price to pay as well for implementing this approach, that is the increased control complexity. We have to realize that in clock cycle number 4, the assumption that the branch was not taken was wrong and potentially conditionally cancel out this instruction. How this cancelling out is done, we will look at later when we look at pipeline control, but this cancelling out has to be done and this leads to additional control complexity. After two subtle ideas, first of two-stage branch completion and the second of assuming that the branch is not taken, we don't seem to have made much headway. The two-stage branch completion has problems in terms of additional data forwarding required, additional data hazard related stalls, and the assumption that the branch is not taken is anyway not going to help for long running loops. We don't seem to have made much headway at all. What else can we do? The next idea we will look at to potentially reduce the branch penalty goes by the name of branch prediction. The idea behind branch prediction is the following. In a running program, the same branch instruction gets executed multiple times, perhaps in a loop, perhaps in a function call, which itself in a loop, and so on. The idea is based on the intuition that whether or not a branch instruction is going to be taken in the current execution is going to correlate strongly with whether or not the branch was taken the last time. It turns out that in most executed programs, there is a strong correlation. So we remember whether or not the branch was taken the last time and use that as a prediction for the current execution of the branch. To implement this, there is essentially a table in the hardware. The first column in the table identifies the PC location corresponding to the branch instruction, and the second column in the table is the prediction corresponding to that branch instruction. In implementation, it is common to use only the last few bits of the PC for maintaining this prediction mapping, because anyway this prediction is a guess and the hardware needs to deal with cases when the guess is not correct. So branch prediction is nothing but a slightly more sophisticated version of the previous solution where we always assume that branch is not taken. Here we are going to assume branch is taken or not taken depending on whether or not it was taken in the previous execution of the same branch. In the simplest possible implementation of the branch predictor, we have a single bit predictor, that is, we simply remember whether the branch was taken or not in the previous execution. If we use a single bit predictor, loops are always going to be mispredicted twice. Can you tell what the two mispredictions are going to be with respect to loops in the single bit branch predictor? A slightly more sophisticated version of the branch predictor is a 2-bit predictor, which remembers not just the previous instance whether or not the branch was taken, but remembers the previous two instances. Well, now can you think of any other way of doing branch prediction? Well, whatever idea you thought of, it is very likely that 100 variations of that have already been tried and many research papers written about those ideas, because branch prediction is a beaten to death research topic. People have proposed even as complicated ideas as having a genetic algorithm running in hardware for doing this branch prediction for a few percentage improvement in the branch prediction accuracy. The last idea, at least among those we are going to discuss in terms of techniques to reduce the branch penalty, is that of delayed branches. A delayed branch is different from a normal branch instruction. That is, the change happens in the instruction set architecture itself. We are changing the meaning of a branch instruction itself to mean something different. Remember that the instruction set is the interface between the hardware and the software, and now with a delayed branch, the hardware is going to tell the software that the instruction after the branch instruction will always be executed even if the branch is taken. That is, the taking of the branch is delayed. and the instruction which is sequentially after the branch instruction, which will always be executed irrespective of the branch condition, is said to be in the branch delay slot. Let us look at an example to understand how this works. Here we have a sequence of 3 instructions: an add, a branch equal, and a subtract instruction. If this branch equal instruction were a normal branch equal instruction, then the subtract instruction's execution will depend on whether or not the branch is taken. Now we are going to change the semantic of the branch instruction to be a delayed branch, which means that the instruction subsequent to the branch instruction will always be executed irrespective of the branch condition. So in this case, the subtract instruction will always be executed, and the subtract instruction is known to be in the branch delay slot. Well, how is this idea going to help? If you recall the example where we had the 2-stage branch instruction and we potentially had to cancel out the instruction following the branch equal instruction in the case the branch was taken. Now with a delayed branch, such a cancellation would not be necessary. That is, the instruction following the branch instruction, which is entering the pipeline before the branch condition is determined, will go through the pipeline anyway and complete its execution. As shown in this timing diagram here, in clock cycle number 4, in the earlier scheme of things, we potentially had to cancel this subtract instruction in case the branch was taken. However, with the changed semantic of the branch instruction, this cancellation is not necessary because this instruction in the branch delay slot also has to be executed anyway, irrespective of the branch condition. So here is a question for you. Who will fill this branch delay slot? Well, add this to the long list of things the compiler has to do in terms of optimizing the code. This is yet another important role for the compiler, filling the branch delay slot. The compiler usually adopts a 2-step process. First, it will generate code as though the branches were normal branches. Then it will try to fill the branch delay slot with useful instructions. While filling this branch delay slot, some constraints have to be obeyed. Let us discover these constraints and how the compiler might be filling the branch delay slot by looking at a few examples. So here is the first example sequence of instructions: AND, SLL, OR and branch equal, and this is the branch delay slot. Look at these sequence of instructions and tell which is a potential candidate for going in the branch delay slot. In this example, the OR instruction cannot go in the branch delay slot because the OR instruction is what is producing the value of R2, which is used in the branch comparison itself. The AND instruction cannot go in the branch delay slot because it would then use a value of R2 which is produced by the OR instruction, and that is not what the programmer intended. So the only candidate that is possible is the SLL instruction can potentially go in the branch delay slot. Make sure you are convinced that there is no problem with the program logic if the SLL instruction here were moved from its original position to the branch delay slot. So in this instance, we are filling the branch delay slot from before the branch instruction. There are 2 other possibilities as well. Let us look at these one by one. The first possibility is to fill the branch delay slot from the branch fall through. That is, the block of code which corresponds to the branch not taken case. Now look at this example and see which of the instructions from the branch fall through can be used to fill the branch delay slot. We cannot fill the branch delay slot with the ADDI instruction, this ADDI instruction. This is because if we did fill the branch delay slot with the ADDI instruction, we have to consider the possibility that the branch is taken. If the branch is taken, then we realize that the value of R5 which is used by these instructions in the branch target will be wrong. That is something which the programmer did not intend. To say the same thing in different words, assuming a branch, a normal branch, if this were to execute, then the value of R5 which is used by the branch target instructions will be something not produced by this add-i. It will be something else. So it is not possible to move this add-i instruction to this branch delay slot. We see, however, that it is possible to move this sub instruction to the branch delay slot. You can look at it and be convinced that this will not cause any problems in either case, that is the branch taken case and the branch not taken case. In both cases, it will lead to correct execution. The third and final possibility to fill the branch delay slot is from the branch target. Now look at this example and determine which instruction from the branch target can potentially be used to fill the branch delay slot. If you analyze, you will find that this add-i instruction cannot be used to fill the branch delay slot because it would then result in this add-i instruction using the wrong value of R2, suppose the branch were not taken. However, using this add instruction to fill the branch delay slot has no such problem. So you can indeed fill the branch delay slot with this add instruction. Among these possibilities for filling the branch delay slot, which of these do you think is most desirable and why? It is always desirable to fill the delay slot from before the branch. This is because the instruction before the branch is always executed. If you fill the branch delay slot with an instruction from the branch fall through, then it is essentially a wasted instruction in the case branch is taken. Likewise, if you fill the branch delay slot from the branch target, it is a wasted instruction in case the branch is not taken. Do you think it is always possible to fill the delay slot? Well, there may be cases where it is not possible to fill the delay slot with any instruction, in which case the compiler simply has to fill a no-op. A no-op is a special instruction which does nothing. It is equivalent to a bubble in the pipeline. So here are the techniques we have looked at to reduce the branch penalty. The first technique was to reduce the time taken for the branch completion from 3 stages to 2 stages. We found that in some cases this helped, in some cases this created other problems. The other technique was to assume that the branch is not taken. In cases when the assumption is wrong, this does not help. The next idea was to do branch prediction. This helps in cases where the prediction is correct and does not help in cases where the prediction is wrong. There has been a lot of effort to improve branch prediction techniques. A technique which is used at the instruction set architecture level is that of delayed branches, where the semantic of the branch itself is changed to mean that the branch will be delayed after one instruction delay. There are many advanced techniques for addressing this branch penalty issue. Let me just mention a few of these. One idea is to use correlating predictors, where the predictor for one branch uses information from the history of another branch instruction. Another idea is that of using a branch target buffer, which in combination with branch prediction not only gives the predicted branch direction but also gives the predicted instruction in the branch target. So there is a small buffer in hardware which maintains the predicted instruction which will be loaded if the branch were taken. And then there are further techniques at the instruction set architecture level, where there are special instructions which can be used for the branch delay slot. This will essentially help the compiler to fill the branch delay slot with these special instructions. These and many more you will likely learn if you take an advanced architecture course. As I said, all of these ideas are subtle and have subtle implications and subtle interactions. Make sure you understand all of these properly before moving forward. The question for you is to determine which of these techniques which we have discussed are complementary to one another. That is, they can be used together with one another to achieve better effect. So in summary, control hazard, simple definition: pipeline doesn't like non-sequential control flow. However, dealing with control hazards is very difficult. Stalling is an expensive solution There are a variety of solutions to reduce the branch penalty, some of which we looked at, and there are many more which we have not looked at.